So let me start this talk with a question. Would you feel comfortable working in such close proximity to this robot here? And the response is probably no, because you will end up like this, or you might end up like this, because most of our current robots are made out of metal, and with that, they're not safe for human interaction. And that's why the reality mostly looks like this of robotics today. So the robots are kind of hidden behind steel cages, and there's an operator outside working with the robot. But obviously, in the future, we would envision something differently. So we envision humans to work collaboratively with robots, that also including interaction and in close proximity. So this is what soft robotics is about, at least partly, and what soft robotics is promising. So this is quite an impressive example of recent years, developed by Pesto. So it has already a lot of degrees of freedom. It has an anti-factor at its tip, so it can do something useful with it. And it looks like it could be almost ready for use in factories already. But there's some, let's say, dirty secrets around there. So what is usually hidden in this box is a whole bunch of stuff for the pneumatic actuation of this robot. So for example, a pressure regulator, an air supply unit, all these kind of things are quite bulky. You need a connection to an air supply. While this still might be acceptable in a factory environment, when you get to, let's say, mobile robotics, or even robots in our daily lives at home assisting us, then that's obviously not acceptable anymore. So this is why robots based on handed shearing auxetics could be an interesting alternative. They consist out of multiple HSA rods, with an architected metamaterial. So here we have 3D printed them with this very particular pattern. And we actuate them electrically using servo motors. So that in the future also promises to be cheap and to be quite small, at least compared to these pneumatic soft robots. And they work in such a way that when you constrain the tip while rotating the base, then they elongate. And when you combine this in a parallel robot fashion, then you can basically get these complex motion primitives of elongation, of bending, of twisting, and so on. So today I would like to talk about how we can kinematically and dynamically model these robots. Then how we can use this model for model-based control. And finally, I would like to show and present some experimental results where we use this model-based controller for set point regulation in a planar environment. So let's start with some quite peculiar characteristics of HSA. First of all, they have a nonlinear elasticity. I will come back to that in a moment. Second of all, they're underactuated. So here we have two actuation, so basically the two motors we can control, but we have three configuration variables which we want to control or guide into a at least stable direction. And finally, we can also notice and observe some hysteresis. So if you look at this first cycle, it shows a quite different behavior from, let's say, the second or the third cycle. So obviously, this is also quite challenging if you want to do model-based control. Now, the question is, how can we deal with all of these problems and challenges? We have developed a concept where we try to take as much as possible out of the toolbox of traditional rigid robotics. So for example, ideas about the kinematics, about Euler-Lagrangian dynamical models, about simple controllers such as PD plus feed-forward. And we want to combine that with, or at least augment this in very particular ways to deal with these specific challenges. So for example, we have a continuum parameterization for the kinematics, and we map into actuation coordinates to overcome the issue of underactuation. I will get again get back to this in a bit. But let's start with the kinematic model. So on the left side here, we have an HSA rod at rest. And when we apply some force in the parallel direction here, then we encounter some actual strain, so basically some elongation. When we apply some force perpendicularly to the top, we will get some shear strain. And finally, when we apply some pure torque, we will encounter some bending strains. However, with these strains, we have only described the strains in the physical rod. But what we still need to define are configuration variables which allow us to define the state of the robot. And we do that by taking this virtual backbone here, which is basically the center line between the rods. And we describe or use the strain of this virtual backbone as our configuration variable. And we have found closed form expressions and mappings to go from the strain of the virtual backbone to the strain in the physical rod. And this mapping allows us to then, for example, to evaluate the elasticity and elastic forces in the rod, which is the most interesting component of the dynamical model in this case. So again, we look at an HSA rod. This time it's first unactuated. And we can model this as a spring with spring constant K0 and a rest length of L0. And then we can, let's say, attach a payload to it with gravity pointing downwards. And obviously what would happen is that we would encounter some actual strain and the rod would elongate. So far, so easy. But what happens when we add or when we actuate the rod? So let's say we twist the top by a specific angle phi, and we constrain the tip. But then we can still model this as a spring, but this time it has a larger spring constant, so this k of phi. And also we have adjusted now the rest length of the spring. So if we don't apply any external forces, it will now be at this rest length of L0 of phi. Again, we can, let's say, attach some payloads to it. And what we will see now is that it will elongate much less because obviously we have a much more rigid rod. So this is the main principle of how we have modeled this actuation. And we can formulate some equations of motion out of that. So we have the very traditional stuff of our dynamical forces here on the left with the configuration variable Q in R3. Then we have obviously some gravitational forces acting. Here we have the elastic forces, but only for the unactuated state. And then we can also add some damping, obviously. And then on the right side, we have let's say, the most interesting bit of it. So for traditional soft robots, or actually for most soft robots, you would find here a multiplication of A times Q. So an actuation matrix multiplied with the configuration. So not with the configuration, but rather with the actuation. So basically we are affine in control, but this is not the case here as we are nonlinear in control. So this alpha is basically a nonlinear function with respect to phi. And second of all, what we notice is that we underactuated. So again, this Q or these dynamics are basically 3 lines, 3 equations, but we can only have 2 variables, phi, to actually influence the forces and torques of these dynamics. We consider the task of set point regulation. So we have a specific desired end-effector position, which we want to reach with our robot. And we start our control strategy with steady state planning. That means that we want to identify a statically feasible end-effector orientation and a corresponding steady state actuation. So basically, when we apply the steady state actuation, we should arrive at this steady state end-effector position with the corresponding end-effector orientation. One option to accomplish this is static inversion. So you formulate your statics, And on the left side, you have your elastic forces and the gravity acting on the system. And on the right side, you have your actuation, and you try to optimize here this desired Q and the steady state actuation such as that these forces perfectly balance. Now we have again the steady state planning here on the left side, and on the right side we add our plant and we perform some inverse kinematics on it. So we basically get our current configuration Q and the associated velocity, and we map into collocated form. So what is this about? We first linearize the actuation function with respect to the planned steady state actuation. And what this gives us is basically an actuation matrix, like we would have it for the traditional soft robots. This allows us then to use the mapping developed by Pietro, presented, I think, about 4 weeks ago, to map into these collocated variables or into this collocated form. And the very interesting part about this is that here in this collocated form, the dynamics, or let's turn it around, the actuation here is directly acting on the dynamics. So when we, let's say, formulate a specific torque we want to apply using some kind of control law, we can then very easily map it into the actuation, and this is quite convenient for us. So what we have here is our current actuation variable and let's say the desired actuation variable, and we do some we compute some error between that in the actuation coordinates, and then we use this within a PID framework. This is kind of a special version where we saturate the integral with the tan-h function between, let's say, -1 and 1, for example. And this represents our feedback action, and the feed-forward action is the already planned actuation, steady-state actuation here. We can add them together, and we apply our actuation to the plant. So this is our control strategy, and now we can use it for performing actual closed-loop control. So what we have here is with the red dot, the desired end effector position, and with the blue dot, the black dot, the current end effector position. On the right side, you have our controller. On the left side, you can find some baseline PID controller, which doesn't use any model knowledge. And as you can see, our model-based controller reached the set point much quicker and also has a much smoother and nicer transient. But we can also do some continuous trajectories. So for example, here on the left side, we are tracking the flame of the TU Delft logo. And on the right side, we are tracking the sail of the MRT CISO. And we observed that this works quite well. What we notice is two things. First of all, we have this kind of small tracking error. This is caused by the fact that we don't have any integral action in the end effector space or in the task space. So basically, if our model is slightly wrong and we slightly have an error in the planning, then this will we cannot basically take this away. And the second thing we notice is that we, let's say, slow down quite a bit. So we sped up this video 3 times, and still the movement was rather slow. So the reason for that is that we have a regulation controller here and not some kind of trajectory tracking controller. So for this to work well, we have to go quite smoothly as we have the static assumptions in our controller here. So in conclusion, we have shown that we can use architected metamaterials to generate complex motion primitives while still staying compliant. These parallel robots often improve stiffness to weight ratio, and this electrical actuation is a very nice property of it, as it will allow us to miniaturize things in the future. And even for this complex robot, we have our dynamics in an Euler-Lagrangian form or model available, which will make just the design of the controller much easier. And with our model-based control strategy, we see a 70% faster response time with respect to the baseline PID controller. We see a 30% reduction in trajectory tracking RMSE, again with respect to the baseline PID. And we do notice that because of the lack of integral action in the task space, we do see some small steady state errors. Okay, so this was everything about this work, but I have some sneak peek about a different work that together with Sonal we just submitted to Robosoft. So we can take the same model and some of the same concepts and design an impedance controller in Cartesian space. So this is really designed for interaction because we can prescribe the stiffness we see in Cartesian space. So this basically keeps the compliance of the system intact, and we can steer the attractor of this impedance controller using brain signals. So here, Sonal here on the steering has this cap on with the EEG sensors, and she's steering the robot in Cartesian space. And in this case, we want to achieve something useful. So we want to demonstrate or showcase one activity of daily living. In this case, it's pressing this button of the hairspray bottle. And what we do is we ask the stiffness to be higher in perpendicular contact direction and to be lower in the parallel direction. And this allows us to apply enough force to press down the button while still making use of this physical intelligence of the system and kind of adjust to the specific structure of the interaction. Okay, thanks a lot for your attention, and I'm happy to answer any questions you might have.
Thanks a lot, Max.